Changes. Turn and face the strain. Changes. Don't wanna be a richer man. Changes. Turn and face the strain. Changes. Good morning, good afternoon, good evening, whatever the case may be. We are continuing our epic study of calculus, which is the study of change. Thank you, Mr. David Bowie, for that. We are talking about the area under a curve, part one. I think there'll just be two parts here. We've been talking about this a little bit in class, so you'll recognize the rectangles, and we were discussing the area under the curve of f of x equal to x squared from 0 to 1. So kind of all this in here. And we talked about how we could use right-handed rectangles and left rectangles to estimate the area under the curve from 0 to 1. And let's see, with 5 rectangles, from the right we got 0.44, and from the left we got 0.24. And then with 10 rectangles from the right we got 0.385 and 0.285. And we're getting closer and closer from above and from below the overestimate and the underestimate to the actual area. Some visuals here. Here's 30 rectangles from the right, 0.3502, from the left, 0.3169, and then 50 gets us even closer and closer to the actual area, which is indeed 1/3. Okay. So how does that work? How exactly does that work? Well, let us consider a curve. And let's find the area under that curve from A to B. And we'll call the curve f of x, so we can talk about it there. And so we're talking about this area right in here. So, oops. There we go. Okay, from here to here. So we're looking at all of the area in here. And we're going to do that by forming the rectangles, and we'll do right-handed rectangles here. It doesn't matter for the purposes of this explanation if we use right-handed or left. So I'm just going to put a few in here. 1, 2, maybe one more over here. And then we could put a whole bunch more in here. And let's see, maybe one here, one here, and then one here. Okay, so we have all these rectangles that we're going to use to estimate the area under this curve by finding the area of each rectangle. To find the width of each rectangle, they're all the same, they all have the same width. All we would have to do is take B minus A and divide it by the number of rectangles n. And we're going to call that width delta x, because eventually we're going to get a whole bunch of rectangles, or even more, a whole bunch, more and more and more and more rectangles. And so this width is going to be changing. It's going to be getting less and less and less, hence the delta. Okay? So we know the width. Each of these points here along the x-axis we are going to name x sub 1, x sub 2, x sub 3, all the way to the very last one right here, which we will call x sub n for the number of rectangles when we're using the right-handed rectangles here. So to find the area of one of these rectangles, we would have to take the length, or the height in this case, times the width. I'm just going to refer to this as length because we generally know the formula for the area of a rectangle is length times width. So to find the length, or in this case the height, all I would have to do is take the f of x sub 1, the function of x sub 1, and that would be the same as the y-coordinate of this coordinate right here. And of course, we already said that the width would be delta x. So the area would be approximately f of x sub 1 multiplied by delta x. And I put the approximate here because I'm going to continue to do these rectangles and we're going to estimate the area under the curve. The exact area of that rectangle, of course, would be f of x sub 1 times delta x. So using the same argument, f of x sub 2 times delta x gives me the area of the second rectangle. And so we would continue that for all of the rectangles that we have until we got to the very last one, f of x sub n, and we would multiply that by delta x. And that would give us, in this case, an overestimate of the area under the curve since we have the rectangles, part of the rectangles above the curve here. Okay. Well, let's consider what would happen if n became greater and greater and greater. In fact, let's consider what would happen if n would go to infinity. Well, what would happen is the width of the rectangles would approach 0. And if it's approaching something, we consider it to be a limit. And if we have the limit, if we can get an infinite number of rectangles under this curve, we can get the exact area under the curve. So I'm going to rewrite this as the area is exactly equal to the limit as n approaches infinity of f of x sub 1 times delta x plus f of x sub 2 times delta x plus dot 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 plus f of x sub n, the last rectangle, times delta x. Now this is just the sum of n terms here. So, well, if it's infinite, but we can rewrite this using summation notation. So this would be the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I, because the I is going to represent all of the f of x's, so to speak, multiplied by delta x. And what we have done is we have laid the groundwork, and we've done, it's not a formal proof, but it's an explanation of the definition of a definite integral. So I'm just going to take this text here and copy it because I've run out of room, and go to the next page so I can give you that definition. And the definition of a definite or integral definition of a definite integral is given thusly. The integral from a to b of a function f of x, a continuous function f of x, dx is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I delta x. And there you have the definition of a definite integral and a informal explanation of where it comes from. Because we could also talk about the left-handed rectangles. There's also other rectangles, but this gives you the basic general idea of where the integral comes from. It is the area under a curve. F of x is known as the integrand. A and B are the bounds. A is the lower bound and B is the upper bound. And if you look back at our little drawing here, you can see A is going to be less than B along the x-axis there. And the other important thing to remember is this integral is a number. It's simply a number because it gives you the area under the curve, which is obviously a number. And so you might be asking, well, why is that helpful to us? And I'm just going to give you a real simple example as to why finding the area under a curve is helpful to us. Here we have what we're going to call a distance problem. We have a car traveling at a constant velocity of 40 feet per second. How far does the car travel over a time of 30 seconds? Well, that's simple. Distance equals speed times time. Speed's absolute value of velocity, so that would be 40 times 30, which is 1,200 feet. Well, if you think about it another way, we have our velocity and we have our time. And let's see, if we're at a constant velocity of 40 feet per second, the graph of that looks like this. Now this graph is not to scale, obviously. And a time of 30 seconds, well, the area of this rectangle that we just formed is equal to 40 times 30, or 1,200 feet, the same as the distance traveled. Writing it as an integral, we would say this is the integral from 0 to 30 of f of t. Now I'm using t because t is my variable on the x-axis. dt is equal to 1,200. And in fact, this is my f of t. F of t here is equal to 40. So we could actually replace that f of t with the function itself, which is 40. Okay, well, no one can drive at a perfectly constant speed because of all kinds of conditions. And here, this might be a bit of a more realistic look at 30 seconds of driving time, with velocity taking every 5 seconds. So if at time 0 the velocity is 25 and 5 seconds later it's 31, and we'll say this is in feet per second, 10 seconds later 35, and so on. If you take a look at my very crude sketch here, if we plot those points, you can see that we don't have a straight line. It's not linear. Most things that we represent with a function out there in the real world, so to speak, are not linear. So if we have a function to describe this curve and we want to know the distance traveled, we could simply find the integral, or the area under that curve, and that would give us the distance. So again, we would have the integral from 0 to 30 of f of t dt would give us the distance traveled. I'll put a d in there just for good measure. Okay, that's it for now. We'll continue with part 2. Until next time.